Hi everyone. So let's try some of the sample problems that are usually asked in the area of CPU scheduling. So first things first, let me show you some of these problems. Take this up, put the following in the chronological order in the context of process execution cycle. If you understand and if you remember the process state transition diagram, the first thing is create the process. This is the first one, and the next one will be the ready state where the process will be ready to execute. The third one is the actual execution on the CPU. Number 3. Number 4 is called as blocking state or wait state, or we can call it as a suspended state if the process needs to wait for some particular action or for particular some event to take place. So that goes number 4. And finally, if it executes successfully, we take it into the terminated state. So this is the order of execution in the process execution life cycle. Let me take the second question. List the two important design objectives of an operating system. And if you ask me, the two main important objectives, while if you want to design an operating system, are the first one should always be user convenience. It should be user convenience, and then the next one should be efficiency. Unless until the user does not feel convenient and it should be easy to use, only then we will use it more. So that is the first design objective. And the second design objective is efficient utilization of the resources. Whatever resources the system has, your operating system should be designed in such a way that maximize its usability. Let me take the third question. Suppose you are asked to choose a CPU scheduling algorithm for a computing system where most of the programs are interactive applications. If you are asked to choose only one scheduling algorithm, which one would you choose and why? So for this, if you want to understand, the best algorithm in such a scenario is always round robin. Round robin is best simply because it does allocate the CPU to each and every process for some stipulated amount of time, which we call it as time quantum. The plus point here is each and every process will definitely get its own share of the CPU at some point of time. No starvation here. So we feel that the processor constantly in contact with the CPU. That is the reason the best algorithm for such scenario will be round robin. Now, let us read this. Assume that there are three processes that are submitted for execution at the same time, and the process A, B, C. So you have to understand the question here. The process A executes for 2 milliseconds, then does IO for 4 milliseconds, once again executes for 3 milliseconds, then does IO for 5 milliseconds, and then exists. So the process B executes for 2 milliseconds, does IO for 4 milliseconds, executes for 2 milliseconds, and then exits. Ultimately, let me write these three things down here so that we can get better understanding. There are three processes, isn't it? A, B, and C. So what about process A? It says that this is exits, not exists. So the process A executes for 2 milliseconds. So it does a CPU execution for 2 milliseconds. And after that, it does an IO for 4 milliseconds. Okay, fine. And after that, it does execute once again for 3 milliseconds. And after that, it does IO for 5 milliseconds. So this is my CPU. This is my IO. Once again, this is my CPU. This is my IO. Now, in case of process B, it executes for 2 milliseconds first, okay, and it does IO for 4 milliseconds, okay, and then executes for 2 milliseconds more, and then it exits. That means it completes its execution. For process C, it executes for 5 milliseconds and does IO for 6 milliseconds, and then exits. The question here is, assume no contention for the resources and the order of execution preemptive priority is A, B, B and C. Calculate the processor utilization with multi-programming. For such questions, the best way to handle it and the best way to calculate the utilization or to understand what's happening is through a Gantt chart. So let me take a Gantt chart here, and remember that we are dealing with three processes A, B and C, and we are having a preemptive priority, and which A is the highest priority process, followed by B, followed by C, isn't it? Now, let me start at time 0. So at time 0, as all of them have arrived at the same time, we can find that A has to go first because all three are readily waiting in the queue. A goes first, which brings to me to the A. So A executes for 2 milliseconds and goes out for IO operations. During this time, B is also waiting here. So next I will allocate the CPU to B, which once again executes till 4. Once again, B goes out for IO operation. Now, once B goes out for IO operation, the only remaining process is C here. So I allocate the CPU to C. C executes till 6. Sir, why did you stop at 6? You have to assign the CPU for C for 5 milliseconds. No, because if you see this, once A completes execution on the CPU at 2 milliseconds and goes out for the IO operation, it completes its IO operation at 6th millisecond. So here A comes back into the queue for CPU. Now at 6, there is A, and once again C is here because A is the highest priority process, and while a high priority process A is waiting, C should not continue its execution. Here C gets preempted. So here I am preempting C. I am removing C from the CPU and I am allocating the CPU to A. Now A starts its execution, isn't it? A starts its execution. Now A requires 3 CPU cycles. If you see here, B has come out of the CPU at 4, isn't it? And does an IO of 4 milliseconds. So at 8, B comes into the queue. But it does not preempt A simply because A is a high priority process which is currently running here. So A continues its execution till 9 because it says 3 here. So first it executed 2, went out of the CPU, did an IO operation for 4 milliseconds, got back the CPU, continued its execution for 9 milliseconds, and it has come out for the remaining 5 milliseconds of the IO operation. After A, B is waiting in the queue. So I assign the CPU to B. B needs for another 2 milliseconds. So B completes its execution at 11 and walks out. Now, if you see here, I already allocated from 4 till 6. That means out of this 5, C has completed 2 milliseconds. So the remaining part of C, which is 3 milliseconds, is allocated here, which completes till 14. Between this meantime, A, which has gone out at 9, once it has done its IO, 9 plus 5 gets me 14, A is executed. Do you understand? So A has come out of the CPU at 9. It has 5 IO operations or an IO operation for 5 milliseconds remaining. It has completed that and it has come out. So at 14, A gets executed. B, it has come out at 11. So B, once it came out at 11, it has remaining, it has got nothing else. So B gets executed here itself. For C, there is still 6 milliseconds of IO operation remaining. The CPU stays idle here because there is nothing to do, and I am showing this idle nature of the CPU simply because only at 20th millisecond C can complete its execution. Now, for me to calculate the processor utilization, I have to find out for this entire duration of 20 milliseconds, for which part of the time is the CPU active. The CPU is active only till 14 milliseconds. So for that, what we get is CPU utilization is calculated as the total time the CPU is busy by the actual time taken for completion of these three processes A, B, and C. So 14 by 20 gives me 7 by 10, which is nothing but 70% will be your answer. You have to understand we did this because we are considering preemptive priority scheduling algorithm. In this case, if there is a high priority process that is executing, you cannot allow a low priority process to enter. or if a low priority process is executing and if a high priority process is waiting, you have to preempt the low priority process. This is the example, and this is how you get the answer of 70% for this question. Let's move on to the next one. So consider a uniprocessor system executing 3 tasks T1, T2, and T3, each of which is composed of an infinite sequence of instances which arrive periodically at intervals of 3, 7, and 20 milliseconds respectively. Once you see that particular statement, you have to understand that you are going to deal with real-time tasks, because it has stored, it is clearly given that each one of these tasks, it is composed of an infinite sequence of instances. That means it comes in periodic intervals. It is a periodic tasks. So we are dealing with real-time scheduling or real-time tasks. It is also given that the priority of each task is inverse of its period, and the available tasks are scheduled in the order of priority, with the highest priority task scheduled first. Okay, fine. In other words, it is describing the rate monotonic scheduling. The lowest the period, the highest the priority, or the highest the period, lowest the priority. Lowest is the priority. The execution time for each instance of T1, T2, and T3 is 1, 2, and 4 milliseconds. And given all tasks initially arrive at the beginning of first millisecond and the task preemption is allowed, calculate the completion time of execution of first instance of T3 in milliseconds. Now, let me write down this particular given theoretical in the form of a table. I have 3 tasks here. So, T1, T2, and T3. It is clearly given that each one of these 3 tasks arrives at a period of 3, 7, and 20. So for these tasks, I am writing the period as 3, 7, and 20. And it is also given that the burst time for these 3 tasks, or the time it takes to execute these tasks, burst time, is 1, 2, and 4. I'm just drawing like this so that it will be easy. My advice to everyone who is working with real-time tasks is that when you want to do such things, I always write down when the task is going to be repeated in the periodic intervals. That means if here the period is 3 for T1, isn't it? So I simply note it here like 0. It comes again at 3. It comes again at 6. It comes again at 9. It comes again at 12, and so on. Because it's an infinite, it is given clearly that it is an infinite sequence of instances. Similarly, T2 arrives at 0, 7, 14, 21, and so on. Similarly, T3, it enters at, it arrives periodically at 0, 20, 40, so on, 60, so on. I write like this because it makes my calculations much more easier. So this is what given, and we have to find out when does the first instance of T3 gets completed. So for that purpose, let us start our working with the Gantt chart again. Now, it is given that you have to take the priority according to the periods. If you check out these 3, the shortest period is for task T1. So it is of the highest priority. The next period is T2. So it has the second priority. And the largest period is for T3, which has the least priority among these 3. So in that order, I'm going to start here. So let me start with at time T0. The first one, the first task to execute is T1, which has a burst time of 1. So it gets done at 1. Okay. So it goes out. So this is done. The first instance of T1 is done, followed by T2. What is the T2? The burst time is 2. So I add 1 plus 2, which gives me 3. So here, once again, the first instance of T2 is also completed. Because at this time, there is nothing else waiting. No, you have to understand that at 3, already T1 entered into the queue, because it is the second instance of T1. So I have to, because T1 is high priority, I have to assign the CPU to T1 only. So next, I repeat the sequence with T1. So T1's burst time is 1. So it gets completed at 4. So this is also done. At 4, now you have to scan the queue. There are no more tasks waiting other than T3. So now you assign the CPU to T3. So T3 keeps continuing. So in order to continue, we will continue until 8. But if you see here, at 6, once again T1 enters into the queue. So you have to preempt T3 at 6, bring this out. So here T3 is preempted. Please remember that. T3 is preempted. Okay. And 2 out of this 4, I have still 2 milliseconds remaining because I only completed 2 milliseconds here. At 6, once again, I have to assign the CPU to T1, which continues till 7 for the 1 millisecond burst time. And at 7, so this is also done. And at 7, T2 now enters into the queue. So I have to assign the CPU to T2 because T2 is higher priority when compared to T3. So T2 goes next, which completes 7 plus 2, which completes at 9. At 9, so now you have to once again see which process are there in the queue. Once again at 9, T1 enters into the queue. You have to compare the priorities of T1 and T3. So T1 goes first because it is of high priority. So I'm cancelling this too. So this is also done. Once again, it is of burst time 10. Burst time of 1, which gives me 10. Now at 10, what are all the processes that are there in the queue? I'm cancelling this also. So there are no other process. Now it is free. So I assign T3. And there is only 2 milliseconds remaining in T3 because the first 2 milliseconds I completed here. So T3 executes or completes the execution of its first instance at 12 milliseconds. So this particular one keeps on continuing as this is a periodic task. All these 3 are periodic tasks. The answer for this is T3 completes its execution at 12 milliseconds. If you are wondering, sir, you only gave me the period and burst time and did not give me the deadline. In such cases, it is always safe to assume that P is equal to D. That means each and every process must complete its execution before the start of the next period. In other words, period is equal to deadline. So it is always better to assume in that particular manner. So this is the answer which gives me as T3 is equal to 12 milliseconds. So let's move on to the next question. So state any 4 competing measures of CPU scheduling algorithms for that are considered for evaluation of algorithms. If you remember, you can say throughput, CPU utilization, response time, turnaround time, waiting time. All these things can be considered as the different performance metrics which we can use for comparison of different scheduling algorithms. List the advantages of MLFQ scheduling algorithm compared with that of MLQ algorithms. Multi-level feedback queue scheduling algorithms are more flexible than multi-level queue scheduling algorithms. Flexibility in the sense that MLFQ is where the process can move between queues. I mean, they can change between different queues of different priorities. That is one very good advantage of MLFQ. In MLQ, there is a chance of starvation for the processes which enter into the queues of low priority. But in MLFQ, you can move this process between the queues so that you can reduce the chance of starvation happening. So these are the advantages of the multi-level feedback queue scheduling compared to that of multi-level queue scheduling algorithms. Let's go to B. Consider a multi-level feedback queue scheduling with three queues numbered as Q1, Q2, Q3. The algorithms used in the respective queues are Q1 with round robin of 8 milliseconds, Q2 with round robin of 16 milliseconds, and Q3 with FCFS. Find, draw a Gantt chart illustrating the execution of following set of process and calculate the average waiting time. So now I am given 3 processes and it's being said that there are 3 different queues here. So just I'm writing it down. Let me assume that this is Q1, which is round robin 8 milliseconds RR8, followed by Q2, which is round robin 16 milliseconds. And the last queue in this particular scenario is Q3, which implements FCFS as the scheduling algorithm. So any process, if you remember the multi-level feedback queue scheduling, any process should always enter into the Q1 first And if it's not executed here, if it's not completing its execution, then it will be brought down into this queue. And once again, if it does not complete its execution in Q2, then it is processed down to Q3. Now let us think, how do we calculate the average waiting time? Once again, the best way to do this is using a Gantt chart. So let me take a Gantt chart here. Once again, I put it as from time 0. Now if you see here, there are 3 processes and only one process has arrived at time 0. At 0, there is only one process in the queue. So I assign the CPU to P1. Now here, in this case, the P1 can be executed until 8 milliseconds, because at 8 milliseconds, P1 has to exit Q1. So this is the execution of P1 in Q1. And 8 milliseconds, though there is no other process, P1 is pushed down to Q2. Because there are no processes in Q1, now we can select Q2 for execution. And once again, P1 will be the same process which will be granted the CPU, because there are nobody else. Because there is no P2, there is no P3 at time 8. This comes at 16 and this comes at 20. There is no other process at 8. I assign the same CPU or assign the same process of P1 to the CPU. Here, this is Q2. While P1 is executing at a time 16, P2 arrives into Q1. If you remember the MLFQ and if you remember priority scheduling, if there is any process in Q1, you have to preempt it. You have to preempt any process, any other processes that are executing which belong to Q2 or Q3. So I preempt P1 here. But please remember that it did not complete the entire burst of 16 milliseconds of RR16. In Q2, it only has completed 8. There is still 8 pending for P1 in Q2. At 16, I assign the CPU to P2. Once again, P2 completes its execution in Q1 till 24. This is Q1. And it will be moved to Q2 because it hasn't completed the execution. By 24, P3 also has arrived into the Q1. So next goes P3, which once again takes till 32. This is Q1. Now at 32, all the processes in Q1 are done. There are no more processes, isn't it? Now we move to Q2. Because P1 is already preempted, which had its share of 8 milliseconds in P1, I continue with P1 here in Q2. So once again, because it's a 60 out of the total 16, RR16, 8 is done here. So the remaining 8 will be completed by P1 till 40. This is once again Q2. You have to remember that at 40, P1 still hasn't completed its full quota of 36. It only has completed 8 plus 16, 24. Now P1 will be moved to Q3. After at 40 milliseconds, P1 has still got some more burst time to complete. So this will be moved to Q3. And next, the remaining ones, P2 will be completed here. P2 is done. Out of the 20 burst time, there is still 12 remaining, which is completed here, 52. This is in Q2. And the only remaining process in Q2 is P3, out of which 8 is already done. There is only 4 left. So for P3, we completed till 56. This is Q2. At this point, all the other processes in Q1 and Q2 are done. There is only one process which is waiting in Q3, which is P1. So which I assign here, which goes till 68. 12 remaining, isn't it? Out of 36, I first assigned 8. And once again, I assigned 8. Once again, I assigned 8. And finally, there is a 24. The remaining 12, I'm doing it here. This belongs to Q3. Now, to calculate the waiting time, what you have to do is, let me do it individually. First, let me calculate for P1. So P1's waiting time is, first it arrived at 0. It is allocated the CPU at 0. So it did not wait for any amount of time. It came out of the CPU at 16 and it re-entered the CPU at 32. So 32 minus 16 plus, if you look at here, it it exited the CPU at 40 and it has re-entered the CPU at 56. So it has waited between 56 minus 40. So 56 minus 40, which is equal to 16 plus 16, which gives me 32. So the waiting time for P1 is 32 milliseconds. What about P2? So you see here, P2 arrived into the queue at 16 and it is granted the CPU at 16. So it did not wait, it's 0 plus it exited at 24 and it re-entered at 40. So 40 minus 24, which gives me 16 again. Finally comes P3. So for P3, if you start, it has arrived at 20, but the CPU is granted at 24. So it already waited 24 minus 20 plus, and it exited at 32 and it re-entered the CPU at 52. So 52 minus 32, which gives me 4 plus 20, which is 24. These are the three individual waiting times of the three processes. Now to find out the average waiting time, you simply do the calculation. 32 plus 16 plus 24 divided by 3 process, which gives me what? Come on, tell me. 24 milliseconds. So this is your answer. This is how you calculate the average waiting time for any given set of process, which uses the multi-level feedback queue scheduling algorithm. Okay, so let's move on to the next one. This is a straightforward question, which is going to give you a list of processes and it is asking you to calculate the average waiting time for each of the following scheduling algorithms. So these are the given set of processes. Let me start directly with the FCFS. And if you remember my earlier videos, FCFS is going to tell you that the process are scheduled in the same order as they are entered into the queue. So the exact order which they enter into the queue is selected for scheduling also. Let me take a Gantt chart for FCFS algorithm. And if I start doing it, let us start with at 0. The first process, I'm going to take the same order which is written here. So P1, which completes at 13, followed by P2. 13 plus 5 is the burst time, which gives me 18. Once again, which gives me, the next one is P3. So 18 plus 23 gives me 41. Next comes P4. 41 plus 3 gives me 44. Next comes P5. P5 is 44 plus 31 is the burst time, which gives me 75. And next followed by P6, which has a burst time of 3. So 78. And the last one is P7, which has a burst time of 14, which gives me 92. So this is a simple Gantt chart where we use the FCFS scheduling algorithm to create this. Now, to calculate the average waiting time, it is easiest done if you calculate for P1. So P1 is equal to, the waiting time is 0. P2's waiting time is 13. And P3's waiting time is 18. P4's waiting time is 41. P5's waiting time is 44. P6 waiting time is 75. It's a straightforward calculation. P7's waiting time is 78. So you do a simple sum of all these things. So 0 plus 13 plus 18 plus 41 plus 44 plus 75 plus 78. How many processes are there in total? Divided by 7. So divide this by 7, which gives you 269 by 7. So the total average waiting time is 32.43 milliseconds using FCFS scheduling algorithm. Once again, please remember that FCFS schedules the process in such a way that whichever order the processes entered into the system, you take the same exact order. If the arrival times are not given in your particular problem, you have to assume that the arrival time is 0 for all the processes. If it is given, you have to take that into consideration and then perform the necessary scheduling algorithms. Okay. So let us move on to the next one. Let's select SJF first. shortest job first. So shortest job first tells you that you pick the schedule, you pick the process which has the least burst time. Okay. And then from that point onwards, you go in an increasing order. So let me just calculate the Gantt chart from 0. So if you find out which algorithms have got the least, or which of the process have got the least burst time, P4 has got 3 and P6 has got 3. But in this order, P4 came first, so I am taking P4. P4, which is 3, P6, which is 6. Now, after these two, the next one is P2, because P2 has a burst time of 5, which gives me 11. After this, so P2 is done, P4 is done, and P6 is done. What are the remaining ones? After 5, if you can see, the next one is 13, which is P1. P1 gives me 24. So P1 is done. And after P1, we go for P7. We go for P7. So 24 plus 14 gives me 38. After this, if you see, there are two left, P3 and P5. The least one is P3, which is 23. So I write down P3, which gives me 38 plus 23, which is 61. And the last one is P5, which is 31. 61 plus 31 gives me 92. So this is how you do the Gantt chart. So once again, if you want to calculate the waiting times, I do it writing individually. So let me just write it down here with a different color, so it gives me much more easier way of understanding. What is the waiting time of P1? It is 11. What is the waiting time of P2? 6. What is the waiting time of P3? 38. What is the waiting time of P4? 0. What is the waiting time of P5? 61. What is the waiting time of P6? 3. What is the waiting time of P7? 24. So in order to find out the average waiting time, you simply write this way. 11 plus 6 plus 38 plus 0 plus 61 plus 3 plus 24, which is nothing but, if you calculate this, it is 143 divided by 7, which gives me the answer of 20.43 milliseconds. So this is the average waiting time when you have selected the shortest job first as your scheduling algorithm. There is one more left, which is your round robin scheduling. And our time quantum is 6 milliseconds. This may take a little bit of time. So if you are given a long list of processes with a short time quantum, I always suggest you to write down the remaining quantum here, so that it will make our job much more easier to understand and calculate how much of the remaining quantum of each process. Let me show you. So let me start from the start. Round robin allocates 6 milliseconds to each one of these process in this particular order only. Let me start from 0. So 0. First one is P1. So P1, I complete the execution at 6. And that means there how much is remaining? 7 is remaining. Next comes P2. P2 does not require the entire 6. So it completes its execution at 11. So this is done. P2 is done. Next comes P3. So for P3, once again, I add 6. I get 17 here. Minus 7 minus 6 gives me 17. Next comes P4. I complete the execution of P4 at 20 because this is also done. Next comes P5. Once again, I add 6. Because the time quantum is only 6 milliseconds, I get 26. And here, I get 25. Followed by P6. P6 is a small quantum. So P6 gets completed by 29. Followed by P7. 29 plus 6 gives me 35. So here I write it down as 8. So this is done, this is done, this is done. My round robin now has to go back to P1 again. So I assign P1 here. So P1, once again I add 6, which gives me 41. So I wrote down now only 1 is left. There is no P2. P2 has already exited because it has completed successfully. Next comes P3. For P3, once again I allocate 6 milliseconds, which gives me 47. This is 11. There is no P4. So after P3, I go for P5. So P5, I get 47 plus 6 gives me 53. And I have to write it down as 19. There is no P6. I move on to P7. So P7 gives me 59. I write minus 6, 2 here. Once again, I move in the round robin order, which gives me the P1 as 60. So P1 is also done. Done. Next comes P3. I add till 66. So this remains 5. Next comes P5. I add till 72. Once again, so P5, this gives me 13. And next comes P7. I only have 2 left here. So I write it down as 74. This is also done. This is executed. So there are only 2 processes left. So I move back to P3. But I only have 5 here. So 74 plus 5 gives me 79. And fine, this is also done. And finally, I have only P5. This because this is a single process that is left in this entire queue. I allocate all the remaining quantums to P5. So P5, 79 plus 13 gives me 92. This is also completed. Now, how do you complete the average waiting time? Once again, if I were you, I'll start writing down the waiting time for each one of the process and then start calculating from that point onwards. Let me start from P1. So what is the waiting time for P1? So it has, the first one is 0. It exited at 6 and it re-entered at 35. So P1 is equal to 35 minus 6 plus it did not complete its execution here. It came out at 41 and it re-entered at 59, isn't it? So 59 minus 41. And you can see at 60 it has completed its execution. So 35 minus 6 gives me 29 plus 18, which is equal to 47. With P2, you can see that it entered the CPU at 6 and it exited 11. It has completed its execution. So for P2, it is 6 minus 0, which is equal to 6. For P3, I'm going to calculate. P3 came in at 11, so 11 plus, and it went out at 17. It entered at 41. So once again, 41 minus 17 plus. So if you calculate, it exited at 47, 60. So 60 minus 47, right? Plus, it still did not complete its execution here. It went out at 66 and re-entered at 74. So 74 minus 66, which is nothing but 11 plus 24 plus 13 plus 8, which is nothing but which is equal to 56. What about P4? P4 came at 17, exited at 20. That's it. It's only one. It has executed only once and did not wait for any other time. So P4 is equal to 17. P5 is equal to, if you take for P5, it came first into the CPU at 20 plus it exited at 26, entered the CPU at 47. So 47 minus 26, okay, plus 47 minus 26 plus, once again it went out at 53 and 66. So 66 minus 53 plus it went out at 72 and it re-entered at 79. 79 minus 72. So if you calculate this properly, what you get is for P5, 20 plus 21 plus 13 plus 7, which gives me 61. What about P6? P6 once again is very easy to calculate. It is 26 because it has only one execution on the CPU. What about P7? P7 is equal to, where is P7 here? It first entered at 29 plus 35, it exited at 35 and 53. So 53 minus 35 plus it exited at 59, 60, isn't it? No. P7, it entered at 72. So plus 72 minus 59. It has closed here. So what I get is 29 plus 18 plus 13, which is equal to 60. If you want to calculate the sum, what you get here is 47 plus 6 plus 56 plus 17 plus 61 plus 26 plus 60, which equals 273 divided by 7. You get the answer as 39 milliseconds. So this is your average waiting time when you consider round robin scheduling with a time quantum of 6 milliseconds, isn't it? Now, let us move on to the next and the last question that we have here. Consider there are three array processes. Once again, if you see at this particular table, you can understand that we are dealing with the real-time processes, P1, P2, P3, and there are the three parameters which actually define a particular real-time process, which we write down here as P1, P2, P3, burst time is 3, deadline is 7, and period is 20. Verify if EDF can be used to schedule the process with the help of a Gantt chart. EDF actually stands for earliest deadline first. This is a kind of dynamic priority scheduling algorithm which is used in real-time scheduling. As I told you earlier, in order to work this problem, once again I make use of writing down the periods at which P1 gets repeated, 0, 20, 40, so on. Here, this repeats itself at 0, here it is 5, 10, 15, so on. This gets repeated at 0, 10, 20, 30, so on. This is my way of handling real-time tasks. So I have to implement now the algorithm of the earliest deadline first algorithm and check whether these three processes can be implemented through EDF or not. Let me once again draw a Gantt chart to see how good or how well we can understand this. I'm going to start with 0 at time 0. You can see out of these three, the first process that should be allocated the CPU is your P2, simply because P2 is the process which has got the earliest deadline. The P1, the deadline for P1 is 7, the deadline for P2 is 5, the deadline for P3 is 8, which is the closest deadline, P2. So P2 goes first. Now, once P2 goes first, you have to check the burst time. So P2 executes until 2 and it comes out. So this is done. Let me change the color so that it is easy to understand for us. So this is done, isn't it? Now, after P2, which should go first? Next should go P1, because after P2 comes P1 with a burst time of 5. 2 plus 3, which gives me 5. Now, if you see here, at time t is equal to 5 milliseconds, once again P2 enters into the system, isn't it? P2 enters into the system. But for this particular P2, if you understand what is the deadline is 5 plus 5, 10. But there is already another process P3 which is waiting inside the queue with a deadline of 8. So when you compare 8 and 10, you should give the priority to P3. So P3 becomes the higher priority process simply because it has a deadline of 8, which is quicker or which is earlier than the deadline of 10 for the second instance of P2. That is the reason here I assign the CPU to P3. So P3 executes till 7. This is done. Now for the remaining other process, 5 is left, P2 is here. So P2 goes next and 9. We have to ensure that whether P2 has reacted with the deadline or not, or whether it has been executed before the deadline or not. The deadline is 10 and it completes its execution by 9. This is also completed. There are no processes in the queue right now. All these three are done. So until 10, the CPU sits idle. At time t is equal to 10, I have got once again P2 and P3, which will enter into the queue. So between these two processes, which has the highest priority? P2, simply because it has a earlier deadline. So P2 goes first at 12. And after P2, once again I have P3, which comes in. So this is done. And now this is also being done, which entered at 10. This is 14. Are there any other process till 40 after at 14? No. So I will wait till at 15. P2 comes into the play. This takes the, so P2 here 17. This happens at 15. So these are the two idle periods of CPU. These are idle. The CPU does not do anything here because it has got no tasks to schedule. And if you now from 17 onwards, you can see once again that there are no more processes left here. So till 20, the CPU is idle. At 20, I have once again P1, P2, P3 entering into the queue. Because the same pattern keeps on repeating, I can say that P1, P2, P3 with the current requirements that are given here, with these three burst time T, D, and P, I can assuredly say that with these three processes can be scheduled using the EDF algorithm. If you want, you can try out for the next step also. You can continue from 20 to 40 also. You will get the same thing. The same pattern keeps on repeating for these three processes with the exact parameters. I hope you understood these problems. And if there are any queries, do ping in the comment section. I would be able to get back to you. Okay. But do try to subscribe and thank you for watching. Good luck.